Okay, now it is. All right. So last time, basically, we did charging of a capacitor. We learned how charges develop, how they're distributed, and their graphs as well. So if you guys have any questions about that, please let me know. Okay. Abu Bakr, learn something from your sister. How many? I never have to ask her to join the class. She automatically does it. Uh, and you?
सर आपने लिंक 4:13 पे भेजी और मैं 4:16 पे कौन से लेट है इधर
बेटा वो मेरा लिंक सेम है. यू कैन जॉइन एनी टाइम. द प्रॉब्लम इज कि मैंने आज गलती से एएस में भेज दिया लिंक. दैट वाज द इशू, राइट? सो कर लिया करो ज्वाइन. इट्स नॉट बिग डील. वही लिंक है जो पहले भी आया हुआ है. ओके नाउ so then today we are going to look at the discharging of a capacitor. This topic was included fresh, so there are not many questions about it, but we will be doing it from other boards and try to make it work. Anyway, so the discharging configuration would be when you connect this switch to this side B. The reason is that now you have disconnected the whole thing, and if you see, now the charges will flow from the negative side and they will end up at the positive side. Is it clear? Like that. While they're doing so, they will supply energy to the resistor R. So this is what is happening. All right. Now, remember this sort of this decay is exponential decay. Exponential decay has a general formula. I'd say that general formula. Let's write it down. Is going to be x equals to x naught e minus t over rc. So this is basically that general formula that we're looking for. Now, with respect to this, I will draw the graphs. So we have obviously the first one, the voltage graph for discharging. We have charge on one plate graph, and then we have current. All right, is it clear, everyone? Okay. Now, when you do this, so you have voltage, you have, let's suppose, time on this side, you have charge, you have time on this side, you have current, and you have time. So all of these graphs, interestingly, have the same shape, just an exponential shape, but they will never touch the x-axis because exponential graphs never do that. All right. So the maximum charge would be V naught, sorry, maximum voltage, and then for the charge, it's going to be the same. It's going to be Q naught, never touches the x-axis, and for the current, it's also the same. Never touches the x-axis, like that. Okay. Now, whenever they're going to ask you about these, what you guys need to remember is, first of all, their formulas. The formula this would use would be V equals to V naught E minus T over RC. This would be used Q equals to Q naught E minus T over RC, and this is going to use I equals to I naught E minus T over RC. Is it clear, everyone?
Yes.
Now we'll see what these really mean. Basically, V in this is the voltage at time t. V naught is the maximum voltage Uh, T is the time elapsed, which means how much time has passed before it started discharging, after it started discharging, and R is the resistance, and C is the capacitance. So this would be it. For the other ones, it is the same. Q is the charge at time t. Q naught is the maximum charge, and the rest of the things are same. Here I is the current at time t. I naught is the maximum current, and then rest of the things are the same. Is it clear, everyone? You can draw this, please. Okay. Anyone who did not get it, please let me know. Samir, everything is good. Patija and Javeria, Zainab, Dania. Okay.
Yes, sir.
Okay, very nice, very nice. Now, so the next thing I'm going to do is I'm going to basically start off with a question. That what type of question you can expect that they would be. For example, a graph shows a discharge current curve. Okay, this graph looks like this, where they have current in milliamperes and then time in seconds, and the graph is shown like that. The maximum current here is 1.7, and at one point where it becomes 0.2, at that point the time is 0.5 seconds. All right, so this is the graph. Now, so the configuration they've shown here is like that. Like this actually. So this is the capacitance of the capacitor is 2000 microfarad and resistance is R. Okay, so this is the question. Now, first of all, they say part 1, find the value of R into C. And then in the second part, they say find value of R. So let's have a look at it. So because this is related to current, I'm going to use the current decay equation, which is I equals to I naught E minus T over RC. Then you see the current at time t was 0.2 milliamps. The current, initial current was 1.7 milliamps. You can read off the graph. Times E minus time elapsed was 0.5 divided by RC. We need to find that. Okay. Now, divide the two values here. So 0.2 divided by 1.7. Milliamp is going to cancel out, and this is going to remain like this. Now, those people who do not take math, they should understand that this function that you see e raised to power some value is called the exponential function. Okay. Now, how do we get rid of this? Basically, we multiply it with ln. Ln is a log, and if you multiply this with the ln, what happens is that x comes out, so it will become x times ln e, where it will become x. Now, why? Because ln e itself is just equal to 1. Would you guys remember this? This is for those people who do not take math and have never learned anything about the logs. Okay, let me see. Now, so to get rid of this e, we're going to multiply ln on both sides. And when we do that, the power of e is going to come out. So ln this is negative 2.14, and the rest of it will be 0.5 divided by rc multiplied by ln e. It's going to be like that. Now ln e, like I said, is just equal to 1. So it means rc will be equal to 0.5 divided by 2.14. This will give me a value of 0.234 seconds. So RC has the units of second. I will explain it in a bit how. All right, everyone.
Yes, sir.
Okay. Now it says we got to find the value of R. So the time, basically RC, is equal to 0.24 seconds, and the capacitance was 2000 microfarads. So we're going to simply divide it, and it's going to be 0.234 divided by 2000 micro is 10 raised to minus 6. So this comes out to be something like 120 ohms. Do you guys understand? All right. So remember this, please. Okay. Now the next. So there's very important value that we need to remember, that's called time constant. Now time constant is basically the time taken for a capacitor to discharge to 37% of its maximum value. Now I'll explain what this 37% is. Right now, time constant is given by the symbol tau, and it is equal to R times C. So this RC that we found is basically time constant. Do you guys get it?
Yes.
Okay, please write this down so I can go to the next page, please. Okay, perfect. Now, so to understand why this is 37%, we're going to learn a small derivation, and from that, we're going to understand what I mean by this. So what I'm saying is, let time t to be the time taken for a capacitor to discharge that is equal to the time constant. Okay, so what I'm saying is the time elapsed this time is equal to time constant, which is obviously we know is equal to RC. Now see this. So if I draw the graph of this, this is, you can draw any graph, voltage versus time or current versus time or charge, doesn't matter. And the graph basically looks like this. So what I'm saying is, if this is V naught, so at what voltage, at certain voltage, let's suppose this is that voltage. Oh my God. This is this voltage V. At this voltage, we're saying that time is equal to the time constant. All right, you people. Now, when I write the equation, it's going to be V equals to V naught E minus T over RC, like that. Since the time on the top side, oh, is going to be, basically I can divide V over V naught like this, and it will be E minus T over RC. And then I can basically simply write, instead of T, I can write RC, and then there's RC underneath as well, so it would be like this. So I just basically put this T like that, okay? Now when RC and RC cancels out, it's going to be E minus 1. Now you can take out the calculator. And in your calculator, I want to show you, your calculator might be a little different from this, but largely they're all the same. So in this calculator, you will see right here, there's a function called EX, as you can see, right, on the screen as well. So your calculator must have this function as well. So you're going to press shift and then you're going to press E, it will come out on that. So let's see that. So if I press shift and E is going to give me E, and I'm going to put minus 1 on top. So this basically gives me a value of 0.37, right? If you notice, this then becomes V over V naught equals to 0.37. So V will be equal to 0.37 times V naught, which I can say is 37% of the maximum value, because maximum value was this, which means that when the discharge has happened to 37%, so this, sorry, 63%, and 37% is remaining. So if we check the time on the graph, it is going to give us a value of RC directly. Do you guys get it?
Yes.
Do you have any question? Yes. No? So basically means when 37% of voltage, charge or current is left in the capacitor, that is when, if you check the value of time from the graph, it is going to give you the value of time constant. And why it is so important? Because that value is equal to resistance times the capacitance, and we can find either the resistance or the capacitance, whatever they're asking for. Get it? Okay. Now, let's look at a question from not this one, but this we will check. We will come back to it after we have done alternating currents. But just a random question that I'm going to write here. Okay. So the question says the defibrillator. It's basically a relator. Okay. So this is basically, you might have seen those already in movies, if not in real life. So the defibrillator passes large current through through the heart for a short time. Okay. Now, it basically looks like this, and then it has a capacitor in the middle, like this. By the way, it has a very it has a very high voltage supply, and it looks like this. So high voltage supply of 1200 volts. This is capacitor 150 micro. This is a switch that we connect from one point to another. This is a two-way switch. And these are like, if somebody is having a stroke or something, or the heart stops functioning, so you might have seen doctors use plates on them, these kind of plates. Have you seen those? These are like these, and they put it on the patient's body, and the person gets an electric shock to revive the heart. Have you seen this machine in movies or something?
Yes.
Yeah, that's the same thing, right? Now, it has a capacitor, by the way. So, now, first of all, we're going to see, it says calculate the charge on the capacitor when it is fully charged. So while I'm doing this, I'm writing the questions. You guys can actually do these questions, no big deal. Part B. When the capacitor discharges, there is an initial current of 14 amperes in the chest of the patient. Now, number one, show that the electrical resistance of the body tissue is about 90 ohms. This is the next part. And then part two, when it says time it takes for 3/4 of charge on the capacitor to discharge through patient. All right. So this is the question. Now, first of all, what do you guys think is the answer for the first one? Yes, go on, please. You got to find the charge. You have the voltage, you have the capacitance. Yes. Anybody? Anyone can do this? Quickly go on, please. It's not a big deal. Do you guys know any relationship between charge, capacitance, and voltage? Now that's very sad. You guys don't know that. Oh my god. You guys have not studied a thing over the weekends. Charge is equal to CV, by the way. That's the first equation I told you about the capacitance. Very bad. The capacitance is 150, micro is 10 is to minus 6, and voltage is 1200. So the total charge that is going to give us is 0.18 coulombs. All right, you people.
Yes.
Now, the next one. When the capacitor discharges, there is an initial current of 14 amperes. Show that the electrical resistance of body is this. Okay, so we got to find the resistance. Do you know any relationship between resistance, voltage, and current?
R is equal to V over I.
Yes, R equals to V over I. The voltage that passes through the body is 1200, current passes 14. So the electric resistance is going to be 86 ohms, like that, which is obviously 90 ohms, about that. And then the next question is the most important one. Now it says, time it takes for 3/4 of charge on the capacitor to discharge through the patient. Okay, I want you guys to please solve this. Try if you can do this. You have 2 minutes for this. It's a very easy question.
So my answer is coming 0.0179 seconds.
Sad life. All right, any answers, please? No.
0.0179 seconds.
Yes, that is correct. That's very good. So all you guys need to learn is that because this is a discharging, so you should be instantly writing this equation. Okay. Now it says the charge is basically uh, reduced by 3/4. 3/4 mean that the charge left would be only 1/4, which is 0.25. Do you guys get it? Just put it inside the equation. Q will be 0.25 Q naught, then Q naught, E minus T, R C, like that. Q naught and Q naught will cancel out, so you're going to get 0.25 and E minus T over RC. Take ln. When you take ln, it will be ln E minus T over RC, and then ln E will be finished, so it will be minus T over RC left. Now, because we need time, so by the way, what you guys need to do is time will be equal to minus ln 0.25. The resistance we found was 86, and the value of capacitance was 150 times 10 raised to minus 6. You do this, you're gonna get 0.018 seconds, just like this. Any questions, anyone? All right.
No.
Okay. Those who could not do this, please write this down so you guys can, learn. And then the next. The next thing is a question that basically repeats in every other part or every other paper, I'd say. Why a capacitor stores energy but not charge? So this question will be there so many times. And now let's have a look. So when you see the plates on the capacitor like this and this, so initially when you look at the capacitors, they have the same type of charges. Like what I mean by this, they're neutral. Like they have equal number of positives, they're equal number of negatives, like that, right? Both of them have the same thing, so they will be called neutral. Now, when one electron enters from the battery, what you guys need to remember, that it adds up to this. So there are more electrons on plate B. So from plate A, because of the repulsion, one electron leaves. Now what's happening? One charge is being added up, one charge is leaving. So if you basically calculate the number of charges, the total charge, there is no change really. So net change in the charge is just zero, because you guys need to understand redistribution takes place. It's not like we are not adding charges on one plate only. The other plate is also losing them. So total remain the same. So how would we write this? We're going to say number one, work is done by the battery that makes negative charges move from move to to plate B. I'm talking about this particular part. Anyway, due to repulsion, the other plate removes one charge from it, like that. So hence a redistribution, so this word is very important, takes place. So net charge remains same. Only the energy is stored. Please write that. Okay. Very good. Write it, write it. If you guys have, if you feel difficulty anywhere, let me know. Samir, you understand everything? Yeah. Okay. Now, you guys, this would be basically all for today. I will then continue tomorrow with more. So I will see you then. Have a nice day.
Thank you.
Bye.
Have a nice day.